Hi everybody, in this video we're going to talk about Prim's algorithm. I'll show you some step-by-step examples and talk about a few applications where Prim's algorithm could be useful. To get us started, let's just talk about what Prim's algorithm is. Prim's algorithm builds on the minimum spanning tree by always choosing the smallest weighted edge that's available. We can think of this as a greedy approach where you're trying to save time, money, distance, whatever's in our application. The algorithm starts with an initial vertex, then the spanning tree will grow by adding edges step by step. Prim's algorithm can be used to help design networks by minimizing the total connection weight used to link all nodes. We might also see it as an efficient spanning tree that ensures all nodes are spanned efficiently with the least cost possible in the network. So let's talk about the steps we take in the algorithm. The algorithm begins by selecting an initial vertex to start building the tree. From the vertex, we select an adjacent edge with the lowest weight. At each step, the lowest weight edge connecting the tree to an unvisited vertex is added. This process is going to repeat until all vertices have been included and the tree is complete. Let's look at a small example to get started. In this graph, we are going to start at vertex A. We have 4 vertices, so we know our tree is going to end up with 3 edges. When I look at vertex A, I see it has 3 connected edges, 14, 12, and 21. We're going to pick the smallest, which is 12. Now that I have 2 vertices to look at, I need to look at all edges connected to those 2 vertices. So I have 14, 21, 25, or 18. 14 is the smallest, so that's what we'll select. My graph currently has 2 edges, and I know I need 3. We've used up 3 of our vertices, A, B, and D, but we need to connect N to C. So we can either use the weighted edge 6, 21, or 18. Since 6 is the smallest, that's the one we'll select. Let's take a look at our final spanning tree. Now we can add up our edges of 14, 6, and 12 to get a total of 32. Let's try that one more time with a bigger graph. In this graph, we're going to again start at A, and I want you to notice that we have 7 vertices. That means we're going to need 6 edges. Looking at A, I have edges of 28, 14, and 15. The smallest is 14. Now I go back to the 15, 28, and I can also look at 13, 9, and 11 connected to C. 9 is the smallest, so we'll pick that one up. From here, I have the 15 and 28 still. I still have 13 and 11, but now I can also look at 20 and 14. 11 is the smallest, so that's our next edge. As we're going through, we want to make sure we don't form a circuit. So anytime we see something that might form a circuit, we'll go ahead and get rid of it, like the 15 between A and B. Now we can look at our remaining edges that are touching A, C, B, or E that won't form a circuit. A has 28, C has 13, E has 20 or 14, but B has a 6, which is the smallest. We again see a potential for a circuit, so let's go ahead and get rid of the 20 from D to E. Taking our next look through the edges, we see 28, 13, 14, or 16, which means we should select 13. If you wanted to, you could get rid of the 28 connecting A to F because it would form a circuit. So looking at our remaining edges of 23, 14, and 16, we can see 14 will connect E to G and give us a spanning tree. To finish up, we're going to add up all of our edges. We had 14, 9, 11, 6, 13, and 14, which gave us a total of 67.